All right. Well, thank you so much for everyone for joining and Ricardo for this presentation. We hope everyone had a really nice summer break and a good start to the fall semester. We're really excited to get going here this October with the GeoDAWG seminar series, and we're very excited for Ricardo for starting us off with a lot of his great work. And since it's been a couple months since our last talk, we'll just kind of give our normal spiel here at the beginning. But the upcoming seminars that we have coming for this fall leading up through AGU are posted on our website, and we've copied them here on the bottom left side of this figure. And as usual, all of these presentations are recorded and uploaded to our YouTube channel. So you can view all of them there too, and we'll link Ricardo's talk. His name here on the bottom left will be a URL to that. So if you want to come back to our website and view this, please feel free to do that anytime. We have a really healthy mailing list where we email out information about GeoDAWG, the upcoming seminars and upcoming workshops and so forth. So if you haven't signed up, please do that at this link here at the top left-hand panel. And then if you'd like to present or know anyone that would give a good presentation here, please let us know. We're looking to fill out starting in 2025. So any examples there would be great. So I'll pass it off to Anthony, who's going to give a more formal introduction of Ricardo's talk now.
All right, thanks very much. Welcome back, everyone. Today we'll be hearing from Ricardo Todling. He's a research meteorologist at NASA Goddard with a background in global atmospheric data simulation, coupled ocean atmosphere data simulation, and forecast sensitivity and observation impact. He'll be talking to us today about integrating GEOS and JEDI and expanding GEOS capabilities for SWDA. Feel free to ask questions throughout, and hopefully we can have a nice discussion. So thanks very much again, Ricardo, for joining us today, and feel free to get started.
Yeah, my pleasure. Thank you. Hopefully you can all hear my voice. Sometimes my sound sometimes fades away a little bit. I guess that's something I've been struggling with for a while. I don't know if it's associated with my laptop fading, so I hope you can hear me well.
Yep, sounds good.
If you need me to repeat anything, I will with no problem. So let me just start by saying and apologizing, I suppose, that I'm not really a space weather expert. I am an atmospheric person and a sort of let's say stratosphere down. So that's sort of my expertise, and particularly in data simulation. But I'm coming from that end, and I've been doing this for a number of years, many years, 30 years, and I'm sort of looking to expand my own abilities and capabilities, and then using our system for that. So and gladly we've been supported in the past year and a half or so to work on this expansion. I'll talk a little bit about that with you. Hopefully many of you have heard of GEOS, the Goddard, the Global Earth Observing System. Sorry, we flipped sometimes of the name, but the Global Earth Observing System from GMAO. So we have a global atmospheric model. And
just to jump in real quick, Ricardo, do you mind resharing your screen and slides?
Oh, what happened here?
That was me. I stole the screen to show our slides, so we now giving it back.
Yeah. All right. So 1 second, and let me just get my act together here. Find the actual Zoom window here. Wait a minute. Here. Okay, here we go. Start again. And good thing I haven't flipped any single slide. So let's see, is it coming? Didn't work, did it? Oh no, it did work. There we go. So come back to the beginning and come back to full screen.
Perfect, thanks.
All right. Okay, so yeah, as I was saying here, so I am, an atmospheric person. So I'll give you a little bit of a outline of the talk. So the talk, so I'll go over, so I sort of a blend of things that I presented before. different instances and sort of more recent work. So which is really toward this extension of GEOS. So, but I'll just give a little bit of a blurb about GEDI as well, because I'm not so sure how much people are familiar with GEDI, but I do know that the space weather community is becoming more and more aware of GEDI. So we just had a workshop in the Joint Center here in Boulder. That was this was a few weeks ago, maybe 2 or 3 weeks ago. That is talking about was talking about GEDI being used for space weather applications. There's already a leg of development in that. So I'll talk a little bit about that, but I'm not so sure how much that has spread yet. So I'll just give a little bit of a blurb about that too. So I'll just talk about DA in general, with just very, very quickly, I guess. And then I'll talk about GEDI. I'll talk about this transition of GEOS into sort of a slowly toward a whole atmosphere model, but we're gonna go in stages. And then I'll just talk about a little proof of concept of an application we just recently did, and then close the talk. So terrestrial weather DA, which is really where I live, I've lived for many years. This is just a plot on the right side is a plot that most of you have seen from ECMWF, showing sort of the years of it's a forecasts for different legs of the forecast. So each one of the colors, different lead times of the forecast, starting from 3 days on the top and then going down to 5 days, 7 days, and so on. This is like the skill of the forecast and how over the so many years, so this is like over 40 years of assimilation, the forecasts have improved quite dramatically, and that's due to the assimilation of observations largely, and also to the reach and sort of the little figure on the left, the little movie on the left is just showing a 6-hour set of observations that are typically assimilated in our weather DA systems, terrestrial weather DA systems. And so that the richness of observations that we have, which is obviously not comparable to anything in space weather, has allowed us to make considerable progress. Obviously, CMWF is ahead of everybody in that, but people, whoever is doing this, is not very far behind in the global context. And so all the operational systems in the world are very much comparable to the EC's skills. So and to the progression as well. For some of us who have been doing data simulation, we can produce figures of similar quality. So an example, for example, in GEOS comes from our reanalysis, and this sort of displays the impact of observations over the course of 40 plus years of reanalysis. And shows, and on the left shows the sort of the increase in observation counts. So these are just counts, and the bottom on the figure is just a relative counts, a percentage count with respect to all the observations in different instruments. And so you see a considerable rise in the observation count, particularly into the sort of so-called EOS era, which is sort of the end of the 1900s. So 1999 was when Terra was launched. The Terra satellite. And so we have, from that point on, really a richness of observations, mainly satellite observations. And the rise continues to actually take place. The figure here gives an impression that there is a bit of a saturation, but that's not really true. It's only true for the particular Merit 2 system here, which is the reanalysis system. From GMAO that all reanalysis suffer from the same problem. We come up with a system, we fix that system, we run it historically, but that system is fixed. So it's hard to actually add new observations to that system. It's something that we typically don't do, and so it gets to a point where the system stagnates and then justifies a new analysis, and that's what we are always working toward when we work in reanalysis problems. So now presently GMAO is working in an intermittent reanalysis, intermediary reanalysis, the one that in between 2 reanalysis. So the upcoming reanalysis will be Merit 3, but there is something that we are working on in the middle here that's called the Merit 21C, which is just a reprocessing of the 21st century observations at a higher resolution than Merit 2. So that's a slightly different application, but And the little movie had shown that was showing that, you know, with time, the observation impact, so the impacts now become sort of a smaller, if you wish, quote unquote, in magnitude. And that just is a consequence of the fact that there's so much more observations, that there's so many more observations that they actually, the individual contributions of them smaller, but they actually are improving, and that's a result of the improvement in the background, just serves the DA system. So and the DA strategy. So so that's a typical situation where showing that the improvement due to the observations. So so with the terrestrial DA, sort of in a sort of broad brush sense, the terrestrial DA, just to talk a little bit about the difference between the terrestrial and the space weather. As you all know, and some of you know way better than I. So terrestrial DA has obviously different time scales and spatial scales. You know, a lot of the stuff that I showed you is done with the global NWP systems, which are sort of nearing the mesoscale scales in the atmosphere. So, you know, the gold, the sort of the real golden thing that we're all after here now is the kilometer scale NWP and corresponding DAs. But nobody's quite doing that yet. So most of our systems are between 9 to 13 kilometers. So these are the high resolution systems that we have operationally running these days, that weather prediction and all that. Then we obviously have also constituent forecasts that are being done. So this is particularly true in GEOS. We actually work quite a lot in doing constituent forecasts. So this is a different beast of problem, because it, you know, it introduces chemistry, and chemistry is complicated and has a complexity of its own, because the full chemistry is a very complex set of equations that involves many species. So the problem becomes very expensive. So you can't really do at full resolution, say at comparable to NWP. It's going to do it at a lower resolution. Same thing for seasonal prediction. Seasonal prediction typically involves a coupled model with the ocean. So an atmosphere and ocean coupling. And those are also costly in many ways, and people need to do many years. And the spin up of these coupled models is a non-trivial business, and so require many years of integration. And again, you know, it's typically done at lower resolution than the resolutions of an NWP system, just from an affordability perspective. All these systems are tending to increase. We're all increasing resolutions in these systems, horizontal resolution and many times vertical resolutions. The NWP systems have gone from rather coarse vertical resolutions to now rather refined vertical resolution. GEOS itself is suffering actually a little bit larger than doubling of its present vertical levels. So we'll talk maybe a little bit more about that coming up. So space weather, on the other hand, and again, you know, this is a point of view from a non-expert here, but you know, somebody who's, so I did a little bit of research, obviously, and read around, and a few years ago, and so I know that, for example, you know, there's the large issues that face space weather. So these very large spatial scales, obviously, and very short temporal scales. So it's very different than the NWP in many ways. And there's this work by Cisco and Solomon from the early 2000s or mid 2000s that really goes over the differences, I guess, and the similarities as well, of the various scales of space weather as compared to the scales of terrestrial type systems. So anyway, and so that these scales, both temporal and spatial, introduce complexities that really have to be thought out very carefully, especially in the context of DA. Nonetheless, people have made quite a lot of progress in implementing sort of these things that have been very largely used and exercised in terrestrial DA. So these various strategies, people have been slowly capable of bringing those strategies into the space weather applications. Most of the applications listed here, though not all of them, but most of them are really small exercises, you know, and not to downplay anybody's work, obviously, but these are complex enough. as they are, but they are not really the full complex set of problems, and there's no way to put the whole problem together at once, as I understand, for space weather. But there is, the multitude of scales and models that cover different seas and different, the ionosphere, magnetosphere, or thermosphere and ionosphere, which is the closest to what we are trying to do. These tend to be sort of more palatable, I guess, when you subdivide the problem in that way. So DA itself, it's a soup of, and I sort of made this little plot based on something in one of the not too old books that came up on data simulation methods by these three guys listed down here. And so I sort of modified that figure a little bit and sort of expand a little bit to sort of illustrate the variety of techniques that data simulation has incorporated over the years. So we've started back in in the 70s. The discussion was really largely focused on sequential versus variational. So the 70s, the 80s, and the 90s, the mid 90s, up to the mid 90s, the discussion was really variational versus sequential methodologies. And then in the mid 90s, there was a proposal for ensemble type strategies by Gary Evanson. I remember being involved in those discussions back then, and I was just coming out fresh of school. And so those things were very exciting, and they looked very unreal at the time, like, oh, this is never going to work, or it's going to be really hard, and et cetera, et cetera. But obviously with time, those ensemble strategies became real. And what really became real to us all is these strategies that we today refer to as hybrid strategies that sort of combine either variational or sequential strategy with ensemble methodologies, and then we have sort of the most sophisticated approaches, and NWP systems, operational NWP systems today use largely a variational hybrid approach, and they differ in flavor a little bit, and in details, what say CMWF does, or what GMAO does, or NOAA, etc. The flavors differ slightly, but it's largely a hybridization of a variational type and an ensemble type. So they've been very successful. Machine learning is something that's popping up, as sort of being, at the moment, I think there's a lot of people, when people talk about machine learning, there is a lot of sort of conversation about the competitor of DA. I think it is funny because, when I think back to the discussions that were taking place back in the 90s, as I said, when the ensemble came up as an approach, and it was exactly the same mentality of a competitive approach, where ensemble would overtake variation or sequential DA, and particularly variational, and that's really not what happened. What happened is that ensemble blamed with existing approaches and turned us into hybridization methodologies. And so right now, machine learning is coming in as sort of, I think it is this competitive approaches, I think, augmented mentality anyway. And I know that for a fact that, particularly for space weather, there's a strong activity. The machine learning is something that's sort of being used quite a lot in space weather, in many respects, a lot more than in terrestrial weather applications. And so, but the way I view it is that I think that these things will combine again and will become hybridized. So I think we're going to have this, in the end, this sort of soup that sort of combines all these methodologies. And right now, today, I mean, there's conversations, there's been, articles published, like one of them being by Alan Gear from ECMWF again, who, essentially discusses the benefits of DA to ML type applications, and the benefits of ML approaches to DA. So I'm particularly interested in the right side here, the ML to DA, and the largest contributions that are being made in that respect within that context are really these implementations of surrogate models. DA, traditional DA, especially traditional variational DA, has had this sort of difficulty of having to develop tangent linear and adjoint models of the underlying nonlinear model. And those things are very, very expensive and complicated. And so one type of surrogate that's been that is now taking shape is to replace those by some type of ML corresponding model. So and then there's other applications too that are cited in that work, and that there's things that we do, for example, for correcting the data, correcting biases and things like the so-called variational bias correction approach. That has also been reformulated such that it can use an ML type application or methodology. So there is a blend, and that's really the tendency, I guess, at least from people who have been doing DA in the atmosphere. The tendency is that we're going to incorporate machine learning techniques, but they're going to be embedded within the structures of what we presently have. And so the thing really is to create a framework that enables us to integrate all these possibilities, all these flavors of DA, traditional DA, and machine learning DA, or machine learning type strategies, to integrate them all into something that can be used by whatever model we decide to have our application developed on. So I kind of give here a very brief outlines of the why for why we want a framework, who's coordinating this, what is it, and how is it done, when is it expected to really replace whatever we presently do, and some connection with the space weather. So just briefly, the why, I won't read the slide here, I'll let you read the slide, but the why essentially is that people have been talking about frameworks for data simulation for quite some time. There's actually a number of frameworks out there. And the discussion took place in various places, various locations, one of them being the CMWF, as you know, because you can imagine, because that's one of the leading groups in weather DA, in terrestrial weather DA. And so they developed, now 15 plus years ago, they started developing this so-called OOPS, which is this object-oriented prediction system. That is a C++ based framework that allows for general applications of DA. So essentially it builds the blocks of the DA, but it is not specific to any model or to any approach for that matter. So it's very general. It's essentially done in a generic sense, and so it allows is a very powerful system. And it took some time for OOPS to be hooked up to real problems. And in the beginning, it was just a small set of example exercises that were available. But eventually, OOPS is now used operationally in ECMWF, for example, and it is a part of GEDI. It's really the core essential of GEDI, and then GEDI builds things around OOPS that are necessary. So who does this? Who's coordinating this? And the official coordinator of GEDI, of this effort for data simulation, is the Joint Center for Satellite Data Simulation, which is largely housed here in Boulder. But it's got its footing in all these other institutions that are the sort of funding partners, NOAA, NASA, NRL, and the Air Force. And they also have informal partners like the Met Office and NCAR, which are that contribute no less than the official partners, the ones financially supporting this. And I just listed very briefly the applications within these institutions, the applications that, or the sort of divisions, I guess, within these that have a lag like at NESDIS, for example, and I have the National Weather Service and the Office of Atmospheric Research. And NOAA, you have had traditionally the Sciences Division, and now with the space weather, sort of, with us starting to look at extending GEOS into something can do that can eventually support space weather applications. The Heliophysics Division is also getting involved. So anyway, so it's a lot of other stuff going on there. So what is GEDI? GEDI, as I mentioned, is sort of really rooted in OOPS, this object-oriented prediction system. That's a C++ based genetic code that provides the pieces for DA. So, like, for example, doing 4D VAR or ensemble data assimilation or ensemble Kalman filter or whatever else anybody else can envision or think of. And it has sort of these objects also, which are abstract objects that also allow that it's sort of associated with the problem of data assimilation. You have a state, you have a model, you have a covariance, you have observation operators, you have observation space, etc. So those things hook up to then things that are sort of a little bit more real, like ultimately being the actual models that run different applications. For example, MUM6 runs an ocean application. So an ocean model, FB3 is an atmospheric global model, and so on. So and also hooks up to real models that are sort of simulate the observations, right? Like CRTM, for example, the community radio tensor model, or RT-TOPS, which is the European equivalent of that. And so all these or operations for doing radio occultation. So these are all observation operators that simulate essentially the observations, and therefore you can then compare with what your model is saying, is seeing. So the real observation can be compared with the model. So these things are necessary components, and so GEDI is sort of the umbrella that sort of embraces all of this. So presently, GEDI can do, is hooked up to a number of models. So this is listed on the far left here in the little table here. So these are all the models. The majority of these models are actually, this table is unfortunately, I think, a little bit incomplete. Sorry, because I actually forgot to add the key important one for the discussion here, for the thing here, which is the sort of there's a couple of ionospheric models that are now being added by NRL to the blend here. So there's the necessary pieces to allow for the components of GEDI to incorporate a model that is in a very non-traditional grid. So all these models that are listed in this application have somewhat traditional grids, in the sense that these are just your typical lat long or some other cube version, but some other slightly common version of breaking up the globe, whereas models for the ionospheric models and things have very exotic grids, like the geomagnetic grids, and so these require slight little modifications in the framework, and those modifications have been implemented by people in NRL with the help from the Joint Center, and so they're making quite good progress on toward this. So yeah, I should have added those here, and I apologize for not doing that. Maybe I'll do that before we post the presentation. And then similarly, observation operators, as I mentioned, which are also another type of model, right? So these are all listed here, and there's a variety of them, and these are necessary because these are what enable us to then do the real operational type of exercise that we're all aiming to do with GEDI. And right now we're working the pieces and making sure that GEDI is capable of doing what it needs to do for supporting our applications. One thing that I will say that, the other thing that I will say is that, the variety of schemes that are presently implement algorithms, really, that's what I mean by schemes, that are implemented that support different flavors of DA. So there's traditional 3D, 4D VAR, but all these other type of ensemble particle filters and whatnot. So these things are all there. There's also a variety of minimizers, data simulation is really ultimately a minimization problem. And so minimizers are an important piece, and it had been in the past in some of our sort of current systems that are sort of a heritage systems, difficult to change minimizers, you know, and some of our systems have put some efforts to actually have at least a variety of minimizers that we can, but it's not that simple to do that in sort of the traditional framework. Whereas in the framework of OOPS is actually rather easy to just go and modify and add a new flavor of a minimizer or something. So it's a very powerful framework. So how is it done? So I will give the example of GEOS. So how are we migrating, or how are we going from the framework that we presently have into JEDI? So I'll just briefly say and mention that GEOS presently, you know, supports a variety of flavors of applications. So some of the most obvious ones, some of the most active ones, I should say, is, you know, our real-time system, or near real-time system, which is a 12-kilometer system, sort of is an NWP type system. We also have, there's also an effort that is very strong at GMAO right now, and has a lot of work being done, which supports an Aussie using a similar system, but tends to run at coarser resolution, 25 kilometers. You know, nothing really else that we do run at the same resolution as the NWP system, just because it's very costly. And also because some of these exercises tend to want to run long time applications, and so long time experiments and things, and so it don't get a very good throughput if you're running a 12-kilometer system. So the reanalysis is another one. The most recent one that I mentioned is the Meta 21C, which is just reprocessing essentially processing observations from the 21st century onwards, so the end of the 1900s. And that's being run at 25 kilometers. So these are all run systems that exist right now. They're all systems that, so the horizontal resolution is listed here, and all these systems are 72 level systems. So we have 72 levels in the vertical. And we are working toward actually changing those levels, upgrading those levels to a set of 181 levels, which should be a considerable improvement in a variety of ways, particularly in resolving the tropopause, the stratopause, and resolving also the boundary layer, which is a very important component in our models. And also, you know, this has been shown by ECMWF, for example, and they actually had a level change from 91 to 137, which is what they use now. And they have shown that the variational bias correction, which is essentially capturing the sort of satellite biases, had improved quite a lot. So anyway, so this is something that we expect to see. So going toward JEDI for us, so, you know, I just, the little figure there sort of depicts a little bit what our systems are. Our system is a blend of, essentially is a hybrid system, as I had mentioned. So most of these approaches are now hybrid. So we run a high resolution 12-kilometer deterministic system that's sort of in the top gray box here. You know, shows an atmospheric analysis, an actual model running, and these systems require or rely on the existence of an ensemble DA system that runs in parallel to this, that provides the background errors of the fundamental pieces that sort of that are necessary for the variational deterministic procedure to work and see well represented errors of the data, let's say, for the variational procedure to do a better job than it would do otherwise, with sort of climatological-like terms. So essentially, the hybrid combines a climatological term with something that flows and changes on a cycle basis. So we cycle the system every 6 hours, and that's what we run. So what we're going to do is we don't want to replace this whole thing with JEDI-based things, because it's really very complicated to do that. So we have a phased approach that will first add, and that's already been done, add an option to do the variational procedure using JEDI instead of that current system, which is the GSI, the so-called grid point statistical interpolation system. So so that would be an alternative. That is an alternative now, and we can run that way, can cycle. That's a good thing to have running side by side sometimes for testing purposes. So that we have eventually, obviously, going to toss that GSI, and that's going to go away. So we're going to have only the replacement of this, and then at this point, we could be literally just go operational with this. But we also want to, and we can do that at any time. It's just a matter of choice, our own choice. Then we want to replace the analysis or the ensemble analysis that's being done in the ensemble component of the system. So we replace those with the GEDI, and ultimately we replace the whole thing, including the workflow. So the gray color is changed to a light gray now to represent the fact that now even the workflow that drives all the decision, puts everything together and make sure that things are available to cycle, even that workflow is going to change. And obviously the only thing that doesn't change in any of this is the model itself. And so these blue boxes here of GEOS, the actual GEOS model, don't have to change. There's no change that GEDI introduces. So GEDI is really just allowing us to do better DA type, and so the more capable, because now we can really test now when we get to this point, or even when we get to this point, we can test different schemes. Although, you know, it'd be easier when you have a workflow that also facilitates changing things in some friendly way. So which the present workflow is not that friendly. So it's old scripts, and it's not really, you know, there's only very light Python based stuff. And so the new ones are very heavily based on Python, modern type. And so anyway, so where, you know, the hosting of this, you know, GeoDAWG is on GitHub, and so many of you have already access. So this is really more here for whoever feels like looking at the presentation can at least have a pointer. So these are clickable, so you go there. So typically GeoDAWG has held the GeoDAWG group, the Joint Center group has held these so-called GeoDAWG academies, which are training type meetings that, you know, bring people together, and then we go through lectures, and, you know, different people from different centers contribute to how to run and what to do, etc., etc. You know, what it is, discuss, you know, if somebody comes with an application, what they have to do to embed their application in GeoDAWG, etc., etc. So we haven't had one in a while, but I think we are there. I know there is already a conversation within the Joint Center to have another one. So it's going to come soon. So for us, GMAO, when do we replace things? We've been, you know, we just replaced this sort of this constant cycle of testing that we've been doing. But, you know, we have still a number of things that are listed on the right side here that are needed to be implemented so that we can truly replace what we have now. We obviously have the challenging, you know, this is the fact that, you know, we are transitioning to a new system, so from the GEOS, so-called GEOS GSI, so the GEOS JEDI. But at the same time, and so in the testing to making sure that GEOS JEDI works the same way that works the way that we expect it to work, that its, you know, its results are going to be either neutral or very light improvement. We really expect to be neutral. So it's a lot of work to just get to that point. And at the same time, we can't just hold back and be only working and trying to replace our present system. We have to continue to develop the present system. That's the left side here, showing the things that we are still doing to the system. And there's a lot of stuff that's going on. But you know, as I mentioned briefly, the level change from 71 to 181. Benefits is that, you know, whatever we do on the left side, the nice thing is you know, a lot of things are happening on the model side with the model changing physics and etc. And physical packages, improve physical packages in various ways. It's all toward enabling the model to then be used for kilometer scale type applications. That's sort of the goal, the grand goal here. And so we don't want to prevent GEOS from developing as we're working in GeoDAWG. So it's a bit challenging because many of us have the hand in both sides. and it's no joke. But anyway, so it's being done, and the good thing is that, as I mentioned, because of what I mentioned, that the model doesn't really change. Many of the things, most of the things that we do will just transfer automatically. Even the model change, the model level change will transfer automatically to GEDI. So it's not really to be of a concern. So extensions to MLT to the sort of mesoscale lower thermosphere type application. So the long-term goal, the long-term plan, or the long-term desire that we have with NASA, Goddard, let's say, is to really exchange GEOS and have GEOS become our sort of whole atmosphere model. So we're going to do this in steps, as the little depiction here shows. This is a little cartoon that I got from Fabrizio Sassi, who is one of the collaborators that I have working on this, or he's the main really PI in many of the things that we're doing when it comes to this. So this is describing sort of the steps that we have. So our first real step here is a modest one, just going to up to about 150 kilometers or so, and that's sort of really the immediate exercise. So there is work already being done to modify and implement at least minimal physics changes that will allow us to do that. The upper boundary parameterization, molecular diffusion, heating and cooling rates need to be adjusted, and the gravity wave drag as well. So these have been done in other scenarios, in other models. Fabrizio particularly has been involved in the Wacom development back in when it was extended, and he was responsible at the time to incorporate some of these changes. So we know and should have the expertise to actually work on this and do this work. So that's what's taking place. So and obviously the ultimate goal is to be able to use this extended model with the MLT model and even the whole atmosphere model into the A-type applications. So some of it will use the most immediate one for MLT. It will be looking at using MLS, for example, or SABRE data or GOLD and other data sets with some other wind type observations as well. So we'll be looking into using these into GEOS. What we have done more recently is sort of, at least we had a little bit of a process of convincing is not the right word, I guess, but it's but I'll use that because I don't have any other word right now. But convincing the upper management that this is something of interest to NASA and that can be done within the GEOS context and all that. So so we've gone through a process, step-by-step process, where we had first sort of just an internal research type exercise, where we were given the opportunity of a 1-year type exercise where we should show that, okay, we can do something toward this. And to do that, we essentially used GEOS as is, no changing levels at this point, and just show that what can we get from this data that, for example, are mesoscale type or mesosphere type data. And so, for example, we know from the MERA exercise, so MERA was the first GMAO reanalysis, not the first Goddard reanalysis, but the first GMAO reanalysis. And so we know from MERA, for example, that we have MERA and MERA2, so these are the two reanalyses. So we know from both of them that MERA, for example, did not have as good stratospheric behavior as it could have, whereas MERA2 did. And that what happened is that in MERA2 we decided to invest and do the research beforehand to be able to assimilate, for example, observations, retrieval temperatures from MLS, microwave limb sound. So we did that. So in a particular example that is actually published elsewhere, show, for example, the zonally average, the temperature at 70 degrees north, and it's showing that this is a period in the January to February of 2006, when there is a sudden stratospheric warming. There's a breakdown of the polar stratopause, And in Mara just essentially goes on merrily without that breakdown, whereas the Mara2 system shows the breakdown rather nice. So we said, okay, well, can we redo this with a more modern version of everything, because both Mara and Mara2 are sort of now a little bit outdated. So we said, okay, let's do this, but let's do this using Sabre, different type of data. So we got the observations, it's not that Sabre hasn't been added to, for example, the GSI system. It has, but we did this independently, and so within the GEOS type framework. And it was just as a proof of concept, really, nothing that would be, it's not new science in any way, but it's just a proof of concept. So we use the observations from data. These are observations that, particularly give us retrievals of temperature, which essentially is what we went after. And just to illustrate a little bit the difference between these two data sets, MLS and Sabre, and I have a couple of snapshots here of 6-hour type snapshots of the observation locations from these two sources. And you kind of, Sabre has this particular little subtlety which MLS doesn't have, which is this sort of this maneuvering of the spacecraft view. And then all of a sudden, your first looks at sort of has more of a southern type view, and then it changes to a more northern type view. So you kind of have to be careful when you're doing the studies like this, like, for example, comparing over that period of the southern one, that you have to have data covering that, because otherwise, it's not going to capture obviously with Sabre. But fortunately, there's a good chunk of that period is actually covered by the northern view of the time-ed Sabre instrument. So we were able to do a little bit of verification with that. So the slides here just show sort of basic work being done to sort of look at, what does it look like? Obviously, make sure that the two MLS and Sabre are somewhat consistent, although we have not assimilated both of them at the same time because it's a bit tricky. But we have either done one or the other. And so, and neither. So we look, for example, at things like, using both data as passive. And so these are sort of globally averaged observation fits. So the dashed means observation fit, and the solid lines are sort of deviations for the sort of O minus Fs, if you wish, or the O minus Bs that fit to the background of the observations. And, they're not too different when they're both sort of being ingested passively over this sort of region of, from 5 millibars to about 0.1. And I know that most of you are used to kilometers rather than millibars, so I apologize for that. But so largely the sort of mesosphere type location, stratosphere, upper stratosphere. And here is a case where MLS is used passively and Sabre is used actively. So Sabre is being simulated. And then the other way around. No, actually, I have this wrong. Sorry, this is actually not true. This is the one that uses MLS as active, and this one is MLS as passive. So I flipped here. So the columns need to flip, and the comment needs to flip. But in any case, so that's what's happening here. And you can see that compared to the first one, as soon as we use, as soon as we simulate one of them, the other one improves just as well. And also, there's an overall, especially in the mean, you can see the mean. Obviously, there's a much better agreement with the data than there was before. So that's a good sign. So then what we did is we repeated the exercise of the Mara versus Mara2 exercise. So we presently have a run that's an official product from GMAO. It's called GEOS IT, which is the IT stands for instrument team. So this is an experiment that we run. And the product of that data simulation experiment is a product that is aimed at the instrument team. So they have instrument teams, the NASA instrument teams have particular preferences and wishes. Sometimes that, they have, typical one, or some what they have, for example, is they have instruments that they're testing, obviously, and then they prefer those instruments not to be included in the experiment, because otherwise it's sort of, it defeats the purpose of having an independent verification for them. So that's what we do. We try to work with them so that we make sure that whatever they want, what they don't want, is in the experiment. And so GEOS IT is sort of similar to our near real-time system. So it is a real near real-time system. It's done at a lower cost of resolution at 50 kilometers actually, which is the resolution of MERA 2 and MERA. So it's 50 kilometers, and but so anyway, so it can be exercised and it runs really fast, obviously, because it's the same with the instrumenting. So, and particularly MLS is one instrument that they don't want to see, because the group from that works with MLS is testing it, so they don't want. So GEOS IT does not have MLS data, and certainly doesn't have SABRE data, and so it's similar to MERA in this respect. So we play the same game here, saying, okay, instead of adding MLS to GEOS IT, it should be the equivalent of doing MERA 2 with MLS. We added SABRE to GEOS IT to see if, again, we would wipe out, or would recover the better representation of the southern the stratospheric southern warming. And sure enough, we do. So it's sort of that's what the bottom figure shows. So the GEOS IT plus SABRE, you can see that sort of a delay of the or breakdown of the circulation there. So ultimately, our goal is to, with this MLT type exercise, this Mesoscale lower thermosphere exercise, is to be able to assimilate a slew of observations and run a reanalysis. So that's not a small feat, obviously. And these observations, by then, we obviously envision GEOS to be a JEDI-based system. So which means all these observations will have to then be incorporated into the UFOs of JEDI, into the so-called unified forward operators. So they, the whatever operators these are associated with, some of them are trivial operators, like the SABRE is a somewhat trivial operator in the sense that it's a direct retrieval of temperature. So it's, you have to be careful with quality control and things like that, but you don't have to, it's not very complicated operator itself. Some of these other ones, sort of radar type ones, or the wind ones, are complicated, and so they'd have to be incorporated, added, and looked at carefully. So just to close, I don't know if I went too fast, or maybe actually it was okay. What we have been doing is just obviously working toward improving GEOS and replacing the current GSI type analysis system with a JEDI based one for our sort of this mesoscale type, this sort of extension of GEOS into 100 to up to 150 kilometers or so. We envisioned a variety of observations going in. The first one being SABRE, which is something that we are working toward teaching the infrastructure of JEDI to understand. So it's the data has to just be put in the proper format, so-called YODA format, which is the format that JEDI understands, which is just essentially right now is the NetCDF type format. But eventually, it will become a more intelligent database. And so that's the present goal. And at the same time, we're modifying, and there's work being done to modify the model itself, the forward GEOS model itself, to incorporate the pieces that will allow us to work with that extension. The analysis system will have to be extended as well, particularly the background error covariances will have to be worked out. And so anyway, and the nice thing is, the last bullet there is the fact that we have just officially been given a goal by NASA, by Goddard, to really and be given the funding really to jump into this project of extending GEOS and moving forward with all that we have in mind here for eventually having a whole atmosphere model with GEOS. So yeah, that's the presentation. If you have any questions, I welcome them. Thank you.
Thank you, Ricardo.
You're welcome, Marco.
I have a quick question, like slide 34, that you have different cadence.
I have
different cadence you listed as different. So slide 34, I think just one before like your vision to assimilate all different kinds of data sets. And then I just like, are you thinking one before 31 there? So cadence. So you are thinking of assimilating at that cadence, and then how does it, you know, like you thinking of 6 hour or 1 hour cycling, and then are you
Yeah,
thinking something like a incremental analysis? I
well,
don't know, like just how are you gonna reconcile this?
yeah, I mean, I mean, we have some of these things, obviously, we haven't completely given, 100% thinking, how they're really going to be implemented, but obviously, um, the hourly ones are a little tricky. And so they'll have to be looked at carefully, and because there's other things that we don't want to upset in the system. So,
Yeah.
hourly is tricky for many people. So, it's possible that we may end up thinking on some sort of a hybrid or combined approach where most things are done at the higher frequency, and then some things are done at a shorter frequency. And then we have to just think about how that tendency gets modified in the model too, because in most of our things, GEOS is a largely dependent, is largely reliant on the incremental analysis update approach. Yeah.
Mhm.
So I think we would have to think about, is there some flavor of IAU that would support a split of the tendency? And
Yeah.
so
that makes sense.
again, it's open. This is the kind of
Yeah,
thing
I know.
it's only gonna
Lots of
happen when
work.
it happens, and nobody knows what's gonna happen. So
Yeah, thank you.
yeah, it's more like the wish list here than the actual display.
Maybe next year. Give update.
Right.
Okay. Went ahead to ask this question, but anybody else?
I don't know if there is a chat. Is something to chat?
Yeah, there's a comment by Tom Berger in the chat.
Yeah, thanks, Ricardo. I just wanted to point out that the Sword Center here at CU is also working with JEDI and WACMX, and eventually, hopefully, WAM-IPE, the NOAA whole atmosphere model, to do a lot of the same stuff. So it's going to be great to work with you guys and hopefully synergistically develop some of these operators and techniques.
Yeah. No, definitely. I mean, I think that's the beauty of JEDI, right? Is that we all benefit from each other's work, and we can definitely divide and conquer here, and so I think that's the beauty of it, and so we have, so it's not even that we are completely sort of competing. It really is a cooperation, I think, because the goals are slightly different. NASA has its own goals, and
Yep.
some of the efforts have different goals. Obviously NOAA has its operational demands. NASA doesn't have that. NASA wants to explore sort of the more of the reanalysis type framework, where we want to understand, the historic component of what happened, and how we can develop things that to the future. And then we, once we can do reanalysis, we can also do OSSIs, and so we want to do stuff like that. So anyway, so it's slightly different goals.
Yep, absolutely. I got to jump off, but thank you very much. Great seminar.
Yeah,
See
no,
you.
thank you, Steve.
Fabrizio had his hand raised.
Yeah.
Zero.
Ricardo, can I ask you a question? Thank you for this summary of the project and all the work that we are going to do in the next 3-4 years. My questions are more on previous slides. For example, on slide 17, you are talking about the model hookups with the JEDI system. And even from the workshop we had a few weeks ago, it's not clear to me yet if it is the model like FV3, Neptune, MOM6 that is brought into the JEDI, or the JEDI that is brought into the model structure. And the reason why I'm asking this is because not only because I don't know the answer, but also because at that workshop I heard concerns from the DoD side that they don't want to share their models within the public. So how is this going to work?
Right. Oh, I think GEDI is actually very well designed to accommodate all of these concerns. So first I'll say that it can be done either way. It can be done completely hidden and not hooked up. So where, like for example, in the little cartoons that I have here, I'm sorry, later on, of GEOS this way, of things happening this way, GEOS is seen here, or depicted anyway, as a completely independent piece. So that essentially the model is never exposed. So if it is, is sharing stuff, the model is never exposed. At the same time, if we choose to do, which we can do, and we already are able to do, is we can actually turn these two boxes here, the DA box and the model box, into a single box that where GEDI drives the model call. Even in that framework, obviously in that framework, if you're gonna, if somebody's gonna run that, they have to have access to the model. They have to have, the model has to be there. So whatever. But that is an option, and that option is a very nice option because it opens up a number of possible DA strategies that are much harder to do if you have two separate, say, executables, as for example, implicitly, shown here. So that the two different pieces. So if you have one single piece, it's much, and typically what that drives the model, and that been in the past concern, especially earlier in the discussions, maybe a couple of years ago, in the discussions with various people, the concern was like, that, for example, GEOS relies in the so-called SMF, which is the Earth Systems Framework, Modeling Framework. So the concern back then was that, what are we going to have to do? Are we going to have to toss the SMF to be able to hook these two things up? And the answer is no. The answer has always been no. And some people, perhaps from lack of understanding, have always thought, or had thought in the beginning that, gee, this is going to be a problem. We're going to, so there was like this sort of big contention, but unnecessarily so, because the reality is that that's not necessary. So for example, we now are able to have GEDI drive the model call, drive GEOS calls. But GEOS changes nothing. GEOS just provides an interface, and it's still a fully SMF type model, has its own thing, nothing's changed in the model. So I think that the obviously the contrary, having the model drive the DA, I'm sure somebody could probably come up with that. I just think, and most DA people think that that's just a bad way of thinking.
Yeah.
But that's open for another discussion. I'm sure that anything can be done.
Yeah. So the first thing you described, having one executable, that opens up a conversation about NeoPsy, right?
Oh, exactly. Yeah. Well, NeoPsy again fits in the same framework, right? So
yeah,
something can be done. So I say NeoPsy is just another sort of component within the SMF kind of structure. So having NeoPsy there or not, it doesn't really matter. I mean, it's okay. It fits within the same context of GEDI can drive the model with all of these other machineries appended to it without any problem.
Okay. Thank you, Ricardo.
No problem.
Any other questions for our speaker? No, not hearing any. Let's all thank Ricardo again for a really wonderful talk. It was great to kick off the fall semester. I think you did a really wonderful job and stayed perfectly on time. Thanks everyone for joining here and asking great questions. And we look forward to seeing you next month for Urch's talk here at our new meeting time of 12 Eastern, 10 Mountain Time. So thanks again, Ricardo, and we will see everyone soon.
Thank you. Bye.
An invitation.